In this video, we are going to talk about Hamilton paths and decompositions of graphs into Hamilton paths and paths. All right, so a Hamilton path in a graph G is a path that contains every vertex of G. So here you can see I have this path with red edges, and you can see it is a Hamilton path. It contains every vertex in the graph. So if you look at this Hamilton path, it is the longest path, right, that is in the graph, because of the fact that if you have a path that goes through every vertex, okay, then if you try to make it longer, you're not going to be able to do that, right? Because of the fact that if you try to go to another vertex, well, that vertex has already been visited, right? And so as soon as you do that, you make a cycle, right, in that graph, the graph of the red edges here, and therefore then it is not a path any longer. So it's a path that you can't make any longer. It's the longest path in the graph itself, okay, if it has a Hamilton path. So if you have a Hamilton path, it will be the longest path in there. And if not, right, then it could be the other way. You could have the longest path in your graph definitely not be a Hamilton path, especially if it's not connected, right? So you can have that very easily. So this is also then a spanning tree, right? The path would be a Hamilton path because a path is a tree, right? And therefore it would also be the spanning tree with the largest diameter, right? The two end vertices in here would be the farthest away, basically, that you could get those. So the Hamilton path, if a graph has one, is the would be the spanning tree with the largest diameter. Okay. All right. So the first theorem that we're going to talk about, not really prove, but just kind of go through the ideas of it, is that the complete graph on an even number of vertices has a decomposition into n Hamilton paths, where n is exactly half the order, half the number of vertices. And here you can see I have such a decomposition for, this is the complete graph on 8 vertices. And what I've done is colored each Hamilton path a different color in here. So you can see this is not a proper edge coloring or anything like that. I just colored the Hamilton path so that they are easier to see in the graph. So you can see here's the blue one. You can see it touches every vertex. The green path as well. All right, and then the red and the black one. So there's the 4 paths guaranteed by this theorem here. Okay, and here you can see, right, that that you could have many different paths of Hamilton paths in a graph, and therefore many different paths of the longest length in the graph itself. All right, so how do you come up with this? It's pretty straightforward, right? Based on the previous theorem that we talked about, we said that every odd complete graph with an odd number of vertices has a decomposition into Hamilton cycles. So for instance, K9, right, has a decomposition into 4 Hamilton cycles. And so here I've drawn that out again. So you can see each of the cycles a different color in here. And then basically all you would need to do is to delete a vertex. Okay. So you would delete the vertex here, and of course all of the edges associated with it. So I just colored them white when I did this, and so just pretend that vertex has been deleted here. I forgot to go through and make its color white so it looks like it's gone. All right, and we already talked about in a previous video that if you delete one of the vertices from a complete graph, then the remaining, that graph is isomorphic to the complete graph on one lesser vertex, okay? Because again, every vertex is adjacent to every other vertex. And so really any bijection, right, between the vertex sets is going to work as an isomorphism. So, all right, and so what that leaves you, right, when you do that is if those cycles, right, I've deleted one vertex out of that cycle and a couple edges, right, out of there. And adjacent edges, right, for that matter. And so what you end up with is, again, a cycle inside there, okay? And those cycle are, not cycle, but path, rather, right? You have a path. All right, and so that path still goes to every vertex that's left, right? And so because we only deleted the edges that were incident with this vertex down here. So there's still there are still paths and they still touch every vertex, so they are Hamilton paths. So you would have a decomposition into, in this case, 4 Hamilton paths, okay? All right, so that's the idea in the proof of that one. All right, and then Theorem 2.3.4 says that the complete graph on an even number of vertices has a decomposition into 2n-1 paths consisting of one path of each length k for k from 1 to 2n-1. So here I have an example, again, on the complete graph with 8 vertices. All right, and so this theorem says that you can decompose K8 has a decomposition into 7 paths, right? One of each length for length 1, 2, 3, all the way to 7. So here we would have a path of length 1, right? That's this cyan colored edge here. You can see, so let's say path of length 1. The pink one is one of length 2. The yellow path is one of length 3. The green path is one of length 4. The red one is one of length 5. If we start here, 1, 2, 3, 4, 5. And the blue one is one of length 6. 1, 2, 3, 4, 5, 6. And the black one is one of length 7. So 1, 2, 3, 4, 5, 6, 7. Okay? So that's what this theorem is saying. Okay? So again, let's walk through the idea of the proof. I'm not going to, don't have every detail filled in, but just enough to give you the idea in this video. What we would do is start with the decomposition of the complete graph on an even number of vertices into Hamilton paths. Right, that was guaranteed by the previous theorem that we talked about. And so here you can see that decomposition. So here I have 4 paths, black one, blue one, red one, and a green one. All right, so there's that decomposition guaranteed by the previous theorem. And then what I'm going to do is, first off, I'm going to keep one of the Hamilton paths. So I'm going to keep the black one, right, intact. So that's the path of length 7 in this case, or 2n-1 in the general case. And then I'm going to break one of those Hamilton paths into 2 paths, one of length 1 and the other of length 2n-2. And so I did that with the blue path. So this cyan is the path of length 1, right? And then I just left the blue path. And so now it has length 6 in this picture, or in this particular case. And then I'm going to go break another Hamilton path up into 2 paths, one of length 2. So that's the one I colored the pink. So I changed these from red to pink. So that's a path of length 2. And then the remaining reds will be a path of length 5 in this one. And then I just keep doing that. All right, next up I take the green one and I break it up into a path of length 3 that I color yellow, and then I leave the remaining edges green. So that's a path of length 4. All right, so that's the idea of the proof on that one. Start with the Hamilton cycles and then leave one intact and then start breaking up the others. And that will give you paths of every length from 1 out to the order minus 1. Okay, the number of vertices minus 1. All right, and that is it on that one.